problem is similar to an interesting Baltic way competition problem. And I'm just going to adopt the approach here that if you have indistinct, non-repeating, I won't write down non-repeating, but you have to account for multiplicities to get the degree in that case. But if you have indistinct roots, that implies the multiplicity is n. Or it implies the degree is n, excuse me. Now again, y'all, I'm not allowing for repetition. If you did allow for repeating roots, you'd have to sum up the multiplicities. I don't want to digress into that too much, but the degree is equal to n here. And technically this isn't correct, but as far as this problem goes, it's correct because you'll get indistinct roots with no repeating roots. All right, so that's what we're going to do. We're going to find the number of roots and then argue that that's the degree. Okay. Now we have a polynomial that meets this condition here. And we want to figure out what its degree is. Now the problem Baltic way, it says find all the polynomials, which I didn't think was that interesting. There's one, and then you can put a constant in front of it. But I think this is a slightly better wording. That's my opinion. Now it's really easy to verify that 138 and 23 are roots of this function, that polynomial that's kind of implicitly defined here. So if you just set x equals to 138 right here, and then x equals to 0 here, it'll wash out that 138 and 23 are roots, and you guys can verify that very quickly. Okay, so we already know that there's two roots, and they're distinct, and so we know the degree is going to be at least 2. Okay, now let's carry on. Now, if you let r be any root of p of x, and I stipulated r is not equal to 138, we'll handle that at the end. Okay, we get this condition right here, which is kind of favorable. Remember, if r is a root, that implies that p of r is equal to 0. And I'll use subscripted r's also here in a minute. But so that's where this all came from right here, right? See, p at r is equal to 0. That's where the 0 comes from, and then whatever r is. There you go. But this implies that r plus 23 is also a root. Okay, this r plus 23 right here has to also be a root since this part is non-vanishing right here. So we get that r plus 23 is a root. So we get kind of this recursive sort of buildup here where r1 equals 23 implies r2 is 46. And so on, all the way up to 115, okay? And so you see we're just hopping along, incrementing by 23. Now notice what happens if we do let r equals 38. If we do allow for r to equal to 138, let me just write right here. If we allowed for r to equal to 138, this part, I'm just substituting in right here, you would get 0 times p at 161. You see, we're arguing for the possibility that 161 would be a root also. Okay. Now where are we? Right? Yeah. Okay. Equals to, we're right here, right? Okay. So we would have, and I put the 138 right here, and this is equal to 0. We see this is identically equal to 0. So we don't know if p at 161 is really a root. So one could argue, I haven't really proved it because this expression is, we don't have information that supports p at 161 is a root. 161 is a root. However, we don't know that it's not either by my way of thinking. So one impression here would be there's an infinite number of zeros. And the only polynomial that would satisfy that would be the constant polynomial equal to 0. Okay, so I could see why that people, I've only shown, we haven't shown that 161 is a root here, but we haven't shown that it's not a root either. So that's a little puzzling to me. I lean toward the fact that we have 6 of them, right? We have 6 roots. We'll list, starting at 21, 2, 3, 4, 5, and 6. In other words, 23 all the way up to 138. In other words, that would be 23K. 23K, K equals 1 to 6. Y'all, that should be a 3 right there. Okay. K equals 1, 2, all the way up to 6. Okay. And y'all, again, this is supposed to read 23K. And so there's 6 distinct roots. Therefore, the degree, this implies that the degree is equal to 6. And notice that's not surprisingly 6 is equal to 138 over 23, which were the two constants present in the original equation. Okay, so you could generalize this. I'm sure I may do that just for the heck of it, see how it works out. But again, y'all, do you see I'm slightly a little bit of ennui, a little bit of discomfort, a little bit of uncertainty here, because this statement just tells us we don't know what P at 161 is, because it's identically equal to 0 irrespective of the value of P at 161. So I haven't shown that P at 161 is not equal to 0. You know what I mean? It very well could be by my way of thinking. Let me know if you see anything wrong with my reasoning. But until now, I'm just going to say the degree is equal to 6 for this particular polynomial. Okay, thanks for viewing.